2, 1. Okay, everyone, let's resume our series of lectures. This is going to be a very fun day, okay? So this is our real analysis 2020, well, 2021 if you want. And this is lecture number 8. I want you guys to pay special attention to the lecture today because it's perhaps one of the most important in this course. I want to discuss with you today about LP spaces. Let's baptize this class LP spaces. A few things you should know. Okay. Oh, thank you so much. You didn't have to do it now, but that's great. Thank you. Okay. Okay, let's start counting. 1 hour and a half of LP spaces. Our setup is going to be, you start with the measure space. Okay, which is going to be a set omega, a collection, a sigma algebra sigma, and a measure mu. Okay? For most of the, we should keep in mind, okay? So we should keep in mind most of the examples that I have in mind are when my omega is something, a certain subdomain of RD. Okay, so let's focus especially on the case of subdomains of RD and mu being the Lebesgue measure. Okay. But of course, we can do the theory for general measure spaces. So what I'm trying to say is that whenever needed, we may assume that our measure mu is complete. If we need the measure to be complete, we may assume it's complete, or sigma finite. Okay, let's see if we need this. Okay, so recall the definitions of the LP norms, right? So recall that for a function, say for f, certain measurable function, let's say taking values on R, or the complex numbers if you want. So you may allow your functions to take real values or complex values. Let's say a measurable function. You may define the following objects. You know, for 1 less than or equal than p less than infinity, you define this LP norm to be just the integral of modulus of f to the p 1 over p. Okay? And if p is equal to infinity, we will define the L infinity norm as being the infimum over all alphas bigger than 0, such that f of x is less than or equal than alpha mu almost everywhere. Okay? So these quantities are perfectly well defined. Okay, I am integrating the modulus of somebody. This is a non-negative function. It may be infinity. This may be infinity. This may be infinity. That's okay. For now, that's okay. But these are perfectly well defined quantities for any measurable function. All right. And the L infinity norm is, you know, it's the, let's say the, written like this, it's the smallest upper bound of the function. You know, the function should be less than or equal than this number, mu almost everywhere. Okay, so in particular, note that we have that the function f of x is less than or equal than its L infinity norm, you know, for mu almost every x in omega, okay? Well, infinity norm is an upper bound for the values of the functions, mu almost everywhere. And recall that whenever we say mu almost everywhere, we say that a certain property holds for mu almost all points. What I mean is that the set of points where that thing does not hold has measure 0. Okay, so we concluded the last class proving, so what we are going to say is that we're going to make a vector space of functions. You know, the functions that have the LP norm finite, okay? We can add them, we can multiply by scalar, and we're going to prove the triangle inequality. This will make these spaces a vector space, a normed vector space, and we are going to prove today that these are in fact complete spaces. You know, these are Banach spaces, okay? So let me just recall where we ended up the last class. We proved what was called Holder's inequality, which was the following. If you give me exponents p, q, r between 1 and infinity, such that 1 over p plus 1 over q is equal to 1 over r, and you always have that if you take two functions f, g, and take the product, if you take the LR norm, this loses to the LP norm, the LQ norm. Okay? Of course, I'm interested in the case where the right-hand side is finite. So if I have a function f such that the LP norm of f is finite, a function g such that the LQ norm of g is finite, then the product fg has LR norm finite, where r is given by this relation here. 1 over p plus 1 over q is equal to 1 over r. Okay? So, so special attention to this. We actually saw that the proof of this, essentially, you can just do the case r equals 1. Then you have exponents p, 1 over q equals to 1. Whenever you have exponents 1 over p plus 1 over q equals to 1, these are called conjugate exponents. Okay? And we actually usually denote this q by what we call p prime. So p prime is going to be always, in the next lectures, whenever I talk about p prime, this is going to be the conjugate exponent of p. That is 1 over p plus 1 over p prime is equal to 1. Whenever you have this case, you know, you have that the norm of f in LP times the norm of g in LP prime always wins against the, you know, the norm of fg1. So remember, this is just the integral of fg. Okay? In this case, so if you take, well, this is what we proved last class. So if you take just p equals p prime equals 2, what you get is known as Cauchy-Schwarz inequality. You may have heard this a lot of times in your life. So this is just a specialization of Holder's inequality to the case 2, 2, and then 1. So you get that the integral of fg loses to the integral of f squared, let's say, 1/2 times the integral of g squared, 1/2. Okay? This is Cauchy-Schwarz. So, and then you can use these things, you know, in a very creative way. Okay? So we are doing this for any measure space. So this could be integrals. This could be sums. If you want to work with the measure space of natural numbers and sequences, this is okay. If you sum the squares of the sequence, sum of the squares of the other sequence wins against the sum of an, bn. If you just take the counting measure on the natural numbers. Okay, so you can be finite sequences, infinite sequences, whatever you want. All right. So we ended up last class proving this. So now our aim is to make this thing into a vector space. Let's see. So whenever you have, I told you, so there are a few properties which are kind of obvious. You know, first of all, if you multiply your function f by a constant c, you take the norm p, then this constant c comes out of the integral in absolute value. Okay? And if you take, you know, f, if this is finite, and a norm p of g is finite, then you can use just the pointwise inequality, say f of x to the p, f of x, let's see what I want, plus g of x to the p. You can just use that this is less than or equal than 2 to the p, f of x to the p plus g of x to the p. You can use a basic inequality like this. Just to guarantee, so this holds pointwise, what any numbers you have a plus b to the p loses to 2 to the p, a to the p plus b to the p. This is essentially trivial, right? So kind of a plus b, if these numbers are non-negative to the p, loses to 2 times the maximum of a and b to the p. This is 2 to the p. And then the maximum of them to the p, of course, loses to the sum of them. Okay, so if you use a basic inequality like this that holds pointwise and you integrate, you see that this integral on the right-hand side is finite. Therefore, the integral on the left-hand side is going to be finite as well. So this means that the LP norm of f plus g will be finite. Okay? Of course, you can take p roots on both sides. And if you treat the case L infinity, is simpler. Okay? But my point is, whenever you have a function f with the LP norm finite and a function g with the LP norm finite, f plus g will have the LP norm finite. So this suggests to us that if we kind of consider the space of functions f such that the norm p is finite, this is a vector space. Right? You can take two functions here. You can multiply by scalars and you still fall in the space. And you can add two functions and you still fall in the space. So you can add things and multiply by scalars. So this is going to be a vector space. If you are working with the real valued functions, this is a vector space over R. If you are working with complex valued functions, this is a vector space over C. Okay? All right. And you have heard me calling this thing in this class the LP norm, right? But is this really a norm? Okay, so remember, we want to make this thing into a norm. So I wanted this to be this thing from the space mapping to 0, infinity to be a norm. But remember what the norm in a space has. So what are the properties that the norm should have? So if you have a vector space, you want to construct a norm in a vector space. Let's call it just V, taking values from 0 to infinity. The norm has to satisfy three properties. Okay? So whenever you have a norm, it has to verify the property that the norm of an element, let's call an element, our spaces are spaces of functions, right? So norm of f is 0, if and only if the function is 0. Second property is that, well, the norm of CF should be equal to C norm of f. And the third property is that you should have this triangle inequality. Okay? So a function from a vector space taking non-negative values is called a norm if it verifies these three properties. The norm of an element is 0 if and only if you have the 0 element in the vector space. You can multiply by scalars in your field of scalars. This is a vector space over a field of scalars. And this C comes out, with the absolute value, let's say over R over C. And you have this so-called triangle inequality, that the norm of F plus G should lose to the norm of F plus the norm of G. I wanted to somehow think of this LP quantity that I define here as a norm. But then, you realize that you have to make a small adjustment, because this thing here is going to be 0 if and only if we have proved this, right? So an integral of a non-negative function is 0 if and only if my function is 0 mu almost everywhere. Okay? So if I am integrating, say, over the real line, I can take the function 0, and I can take the function that is everywhere 0, but at the point 0 it's 1, at the point 1 it's 1. I mean, these two functions here on the real line will both have integral 0. But in principle, they are different functions, if you want to consider really a function as a pointwise thing. So in order to have this claim, to have this being a norm, we have to make the identification of functions that are equal mu almost everywhere. Okay? So this is what we do. So from now on, we identify F and G. So we say that F is the same as G if, so we identify F and G if F is equal to G mu almost everywhere, okay? So if two functions are equal mu almost everywhere, meaning that the set of points where they are different has measure 0, okay, then I will say that the two functions are equivalent, okay? This might be tricky, okay? So if you are working with the Lebesgue measure, you kind of know what it means. But if you have a measure on the real line that has a delta at a point, so the measure of a point is really positive, then the functions have to be equal in that one point, because that point is a set of measure, a positive measure, right? So be a little bit careful with this. But whenever two functions are equal mu almost everywhere, I will say that these are equivalent. So this is an equivalence relation, Of course, F. So you can call F equivalent to G. So of course, this F is equivalent to F. If F is equivalent to G, then of course G is equivalent to F. And then if F is equivalent to G and G is equivalent to H, of course F is equivalent to H. Union of sets of measure 0 still has measure 0. So if F disagrees with G in a set of measure 0, and G disagrees with H in a set of measure 0, F disagrees with H at most in the union of the two sets, which still have measure 0. So this is what we call an equivalence relation, and it splits my functions into equivalence classes. Okay? So I can take the equivalence class of the function f. The equivalence class of the function f are all the functions that are equal to f mu almost everywhere. Okay? And then I can actually take I can define, I will write this just once, but we can actually define the LP norm of the equivalence class of f by just saying, well, this is just the integral of f to the p in omega, right? This is if 1 less than or equal than p less than infinity. And what the infinity is the usual modification, right? And you can define this to be the LP norm of the equivalence class Because it doesn't matter which element of the equivalence class you take, it gives the same integral. If two functions are equal mu almost everywhere, their integral is the same. Okay, so the norm is something well defined on these equivalence classes. Okay, so the LP space, which we call, is the set of all equivalence classes which have finite LP norm. Okay, this is the definition. So this is the definition. Space LP, which we may simply denote LP, or we may denote LP of omega sigma mu, is the vector space of equivalence classes F for which LP norm of F is finite. Okay, so this is this vector space. This is vector space of equivalence classes for which the LP norm is finite. Okay, of course, I can, two things here which are basic. I can add two functions. The equivalence class of F plus G is the equivalence class of F plus the equivalence class of G. Again, you will just use that the union of two sets of measure 0 has measure 0. And the equivalence class of a constant multiplied by your function is this, the constant multiplied by the equivalence class of the function. So you can really add up equivalence classes and multiply by the scalar. So this actually makes it into a vector space too. But from now on, we will just forget this. This will be always in the background. Functions that are equal almost everywhere are identified, but I'm not going to be writing. I'm just going to abuse the notation and write and keep writing this LP norm of F. But now I'm in an equivalence class. Okay? Now, with this in hand, with this adjustment, my function norm P from LP to 0, infinity, infinity, open, right? I'm not taking infinity here because LP is the set of classes, the set of functions such that this norm is finite. So this now, in fact, verifies the property. Well, if a function is 0, then my function, if norm is 0, my function is 0. But now my function is 0 almost everywhere, okay? Remember, almost everywhere. Second, I'm okay. I can multiply by a scalar, and the scalar goes out. Okay, so this is almost a norm. We just have to prove the so-called triangle inequality. We haven't proved this yet, but we made the adjustment so that the first property of a norm, that the only element that has norm 0 is the 0 element, now it's a well-defined thing. Okay. Okay, so on top of Holder's inequality, the other very important inequality that you should know is this one. This is called, let's call this proposition 1 of the class today. So this is called Minkowski's inequality. Minkowski's inequality. Or simply the triangle inequality. So my claim is, if for all 1 less than or equal than p less than or equal than infinity, you have f plus g to the p less than or equal than f to the p plus f and g belonging to LP. Okay, so if you have any exponent between 1 and infinity, possibly infinity, two functions in LP, okay, such that this is finite, then this thing. Proof. Let's see how we prove this. The proof goes as follows. We are going to do the following. Pointwise, we have the following inequality, you know. So let's just take, so the case infinity, the case p equals infinity is easy. I'll let you to think about it, you know. Because if this is infinity, the LP norm, if this is less than alpha, this is less than beta almost everywhere. Of course, the sum is less than alpha plus beta almost everywhere, okay? So let's think about the case. Let us consider case 1 less than or equal than p less than infinity, which is really the hard one. And what you do is that, okay, so you take if you take at a point x, you're going to use the following thing. Okay, so f plus g to the p, this loses to, you know, f of x plus g of x times, you know, f of x plus g of x minus 1. Okay? So I take this p and I split it into 1 and p minus 1. And the 1, I use the regular triangle inequality here to say that the absolute value of a plus b loses to the absolute value of a plus the absolute value of b. Okay? All right, so you just write this as f of x times this other quantity, f of x plus g of x, plus g of x times minus 1, and this is again f of x plus g of x. Okay? So the idea now is to use holders. So we are going to use holder. So we are going to use Holder's inequality with the conjugate exponents, 1 over p plus 1 over p prime equals to 1. So if you have exponents 1 over p prime, and these add up to 1, you can actually solve for p prime if you want. So 1 over p prime is 1 minus 1 over p. We can solve this. We get p minus 1 over p. So this means that my p prime is p over p minus 1. So this is my exponent. So by holder, what I get is that the integral of, let's use it right here, f times f plus g to the p minus 1. So this is my function. This is one of the functions f, and this is this plays the role of the g in the holders. Okay. So the integral of f times g loses to the norm p of f. I don't have to put absolute value of f because the norm p already is the integral of the absolute value of f. Okay. Times the norm p prime of this function here, f plus g to the p minus 1. Okay? Let's just see what this is. Let's make a side calculation here. And let's see what this is. So this is the integral of my function, which is f plus g to the p minus 1, raised to p prime, everything raised to 1 over p prime. This is the p prime norm, which is the integral of f plus g. Now, remember, p prime times p minus 1 is just p raised to 1 over p prime. And then you make an adjustment here to make the LP norm appear. So this is f plus g to the p to the 1 over p. So this is the LP norm, everything raised to, but you really wanted 1 over p prime, so you have to cancel out this p here outside and put over p prime. So this is really f plus g, the LP norm, raised, this is the LP norm inside, raised to the power p over p prime. Okay? So this is equal to LP norm of f, and then f plus g, p norm, p over p prime. Well, you do the same for the other one. The other one is exactly the same. Okay, so this is going to be less than g to the p, and then this f plus g p prime, and you just add them up. You add these two. So when you add these two, and you use this inequality here, so what we are doing is that we are kind of integrating here, 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 and here, right? So on the left-hand side, what is this integral here? On the left-hand side, so you sum, and you get that this is f plus g, the LP norm, raised to the power p. Okay, so be already very used to this thing. Whenever I write the LP norm raised to the power p, remember, the definition of the LP norm has a power 1 over p. Okay, so whenever I integrate this, you should immediately recognize, okay, this is the LP norm raised to p. This is going to lose to the integral of these two guys. Well, but this integral loses to this integral loses to that. So what I get is this common factor here. So I get the LP norm of f, the LP norm of g, multiplying this common factor, f plus g, p prime. Okay. Now, you would like to cancel this with this. You can do it, provided it's not 0. So let's go back to the very beginning. If this LP norm of f plus g is 0, your problem is done. You have nothing to prove, right? So perhaps we should say in the very beginning, let's consider this and assume that f plus gp is not 0. Because if it's 0, we are done. Now, if this is not 0, you can cancel. Okay, so you get on the left-hand side the LP norm of f plus g raised to the power p minus p over p prime. It's less than. Let's just take a look at what this exponent is. I bet it's going to be 1 because it has to work. But let's verify. So p minus p over p prime is p minus remember, p prime is p over p minus 1. So you get p over p minus 1. Cancels, so you get p minus 1, which is 1. Okay? So this exponent here is just 1. This is your inequality. Okay? So this is how you prove Minkowski's inequality. It's just a basic application of Holder's inequality with the conjugate exponents. Is that okay? Well, yeah, I don't see any angry face, so I assume it's okay. I don't see any angry face, partially because of the masks, so I don't see it anyway. Remark. I let you think about the cases of equality. When can we have equality in this inequality? You know, for the triangle inequality, if you add up two numbers and you say that the modulus of, there are cases of equality, right? So if you add up two numbers, a plus b, and you say this is less than the absolute value of a plus the absolute value of b, is somebody with the, hello, we have noise here. Somebody's with the microphone open and moving stuff. Please mute yourself. Okay.
Collinear FMG, if collinear vectors, collinear functions, then equality holds.
Yes, so if the vectors are aligned, right? In case of real numbers, if the two numbers have the same sign, then this will be equal. So we really have to use that the two numbers or the two vectors are aligned, they have the same sign. We have to think about it how we would like to have it here, you know? Because here we used a triangle inequality. In the very beginning, we just took this P and we split this P into P minus 1 and 1. That's not, we're doing nothing, but this one, we got a modulus of F plus G and we split, we said it's less than or equal to the modulus of F times the modulus of G. Okay? And this would have to be the same. Okay? Okay, maybe this is not, this is not in the microphone. This is really behind the room, I guess. There's nothing we can do. But now, look. Yeah, think about it when this could be. So we need equality here, okay? But we also need equality in Holder's inequality right here. But we need all of this to make it happen, okay? So I'll let you to think about of quality, okay? My guess is that you should have F being equals to C times G. Guess is that you should have this for some non-negative. Okay? But think about it and let me know. That the equality would only happen if F is equal to C times G, of course. This is all mu almost everywhere, because we were talking about equivalence classes. Okay? For some, well, this is if the functions are, real valued, but if the functions are complex valued, they should also be aligned. So yeah, my guess would be this. Check out and let me know if this is true. This is sufficient, definitely sufficient, right? So if you have F to be C times G, you can just plug in there and you see that the equality happens. My claim is that maybe this is true if and only if F is equal to C times G as equivalence classes for some non-negative C.
This implies Gilder's inequality because Gilder's equality case occurs only and only if two vectors are collinear.
That is true, but you know, this is true pointwise here. But if you have just real numbers, I mean, they could be all positive. If at this stage here, if F and G were, at this first stage, if F and G were just a positive, you would get equality here, you know? You would get equality up to here, okay? So, but they could, if they were only positive, they didn't have to be multiples of each other. But then you have to also think about when equality happens here. Before we go on, let's move on. We think about it a little bit more. I'll let you think about this case for a little bit. You should also think about when equality happens in Holder's inequality as well. Okay, so think about the case of equality in Minkowski, and think about the cases of equality in Holder's inequality. These are two exercises for you. Moving on. Okay, so we have succeeded in making this space a normed vector space. So now my LP is a normed vector space. Right? My LP is a normed vector space. Okay? It started just as a vector space. When I considered the equivalence classes, we proved the triangle inequality, which was the last remaining piece to prove that this is in fact a norm. So we have a norm. Okay? And now we are going to prove that the space is what we call complete. This is what's called a Banach space. It's a complete normed vector space. So this is the theorem that we prove next. Sometimes known as Rees-Fisher theorem, which is LP is a Banach space. And here 1 less than or equal than P less than or equal than infinity. Can you give me an example of a normed vector? So complete means, so don't forget, complete means that every Cauchy sequence, in case you have never seen this, every Cauchy sequence converges. Every Cauchy sequence, say AN, converges to an element of the space, right? That's the catch. It has to converge to an element of the space. Then I say that my space is complete when every Cauchy sequence converges to an element of the space. But professor, what is a Cauchy sequence? I've never seen this. Well, a Cauchy sequence, really, you can just think about Cauchy sequences in a metric space here if you want. But let's say in a normed vector space. So a sequence is said to be a Cauchy sequence if for every epsilon bigger than 0, there exists a certain number, let's call n0, which is n0 of epsilon, depends on this epsilon, such that AM gets close to AN in norm, it's less than epsilon, for all pairs of numbers m and n bigger than this n0. The sequence are if I give you an epsilon, there exists an index n0 such that when your indices m and n are bigger than this n0, the elements am and an are very close. Our distance is less than or equal than epsilon. So you see that the sequence somehow wants to converge. Now it's just a matter of proving that it converges to somebody which is in the space. For example, can you give me an example of a normed vector space that is not complete?
We can Q rational numbers.
Yes.
Over the field of Q. Q is field, so we consider Q on the own, one-dimensional space.
So the rational numbers are a vector space over the field of rational numbers. So you can take rational numbers and add them up. This is a rational number. You can multiply by a scalar in the field, in Q. This is also a rational number. So this is certainly a normed, the norm is the usual absolute value, so this is a normed vector space. But it's not complete, because you can take sequences of rational numbers that will converge to a real number. And so this, the limit
Irrational number.
The limit will leave the space, you know? It's not going to be an element in your space. So the rational numbers are an example of a normed vector space that is not complete. The real numbers, on the other hand, are an example of a normed vector space that is complete. So we are going to prove that LP is actually complete. So if you have a Cauchy sequence in LP, it will converge to an element. The elements here are functions, right? It will converge to another function in the space. Let's do it. This is so much fun. All right. Proof. So what we have to do is to prove that every Cauchy sequence converges. All right, so let's treat the cases p equals infinity and p equals 1 separately, okay? So let's do first the case 1 less than or equal than p less than infinity. So let me do infinity later. Okay, so consider a sequence of functions, let fn n bigger than 1 be a Cauchy sequence. This is actually going to be a very good exercise for you guys to test some of the things that you have known up to this point, okay? So start with the Cauchy sequence. So this means that this definition holds. For any epsilon, you find an index n0 such that fm and fn in the norm now, which is the LP norm, loses to epsilon. Okay, so let's write again the definition. So then, for any epsilon bigger than 0, there exists an index n0 such that n0, which is n0 of epsilon, such that if m and n are bigger than this n0, then you have fm minus fn less than epsilon. Okay, so now what I will do is I'm going to start taking this epsilon to be 1 over 2 to the k, where k is equal to, say, 1, 2, 3, well. Okay? So when I take epsilon small, so if I take epsilon, say, 1/2, okay, I find a certain index n0, which such that this works for 1/2. So whenever my indices are bigger than 1/2, this is less than epsilon. And then I do it with 1/4, and I pick a function. So my claim is that if you take epsilon equals to 1 over 2 to the k, you can find, we can find a subsequence, let's call it gk, a bigger or equal than 1, of fn. So it's a subsequence such that, let's put it, gk plus 1 minus gk is just less than or equal than 1 over 2 to the k. This is the LP norm, right? This is the norm is the LP norm. Okay? So for example, if k equals 1, you get 1/2. For 1/2, there is a point where for all pairs of function bigger than a certain index, the difference in the LP norm loses to 1/2. So you pick that first index, call it G1. That's good. And then for 1 over 4, you pick something that comes later. So you pick the index that works for 1/2, you call this function G1, and then the index that works for 1/4. It's probably an index n0 much later. You call this function G2, the index that works for 1 over 8, you call this function G3, and so on. So you have this property that since these two functions win against this index, the index here, G2 minus G1 is less than or equal than 1/2, G3 minus G2 less than or equal than 1/4, and so on. Okay. So think about this construction. It's not so hard to think about. Okay, so once you construct this subsequence, what do you do? Well, now let us do the following. Let us consider the following function, h, let me call it hn of x, to be this function g1 of x in absolute value plus the sum k from 1 to n minus 1, let's put it here, of gk plus 1 of x minus gk of x. So let's consider this function. Let's call it h big N, and let's say for n bigger or equal than 2. Doesn't matter. For each point x, I am summing the absolute value of this g1 plus the sum from 1 to n minus 1 of gk plus 1 of x minus gk of x in absolute value 2. Okay? So it's clear from my definition, that this sequence here, hn, is an increasing sequence. Because I'm just summing positive things, and whenever I move from n, big N, to big N plus 1, I include more things in my sum. Okay, so it's clear that this h2, it's clear that all of these functions are non-negative because I'm just summing up absolute values. And for every point, h2 loses to h3 of x, loses to blah, 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 blah. Okay, so for every point x, this is an increasing sequence of numbers. It could possibly be infinity, no problem. Okay, if just g1 of x is infinity, of one of these guys is infinity and the other is not, this could be infinity, that's okay. But whenever you have a monotonically increasing sequence of real numbers or infinity, this sequence certainly has a pointwise limit. Okay, so let h of x being the limit when n goes to infinity of hn of x. Okay, so this is the limit. There is no question about this function being measurable, right? So each hn is measurable because the absolute value of some measurable function is measurable. I'm summing up measurable functions, so each of them is measurable. And also a limit of measurable functions is measurable. So this function h that I constructed here is measurable. Now, we can use, let's use Fatus lemma. If I use Fatus lemma, what I get is that the integral of, let's say, h, the p norm, 1 over p, loses to the limit, when n goes to infinity, of the, you can write it like this. Using Fatus lemma, you get that the LP norm of h loses to the limit infinity of the LP norms of these hns. Right? So that's the integral. Remember, Fatus lemma was the integral of the limit of somebody loses to the limit of the integrals. Okay? So I'm using integral of the limit of the functions actually hn to the p, and this is the function hn to the p. And the integral of the limit is, well, the sequence has a limit, so the limit is actually h. So this is the integral of h to the p, loses to the limit of the integrals of hn to the p, and then I take p roots on both sides. All right, so you get this. Again, it's important to know when to use these three core convergence results: Fatus lemma, monotone convergence, and
dominated convergence.
Dominated convergence. As a matter of fact, here you could also, if you wanted, you could actually use monotone convergence here. I don't have to use Fatus Lemma. I can use actually monotone convergence if I want to say that this is actually equal to the limit of these things. Okay? The sequence is increasing, right? By monotone convergence, this is actually equal. I just needed the inequality given by Fatus Lemma. So, I mean, there are occasions, such as this one, where you can use more than one of the results, okay? But monotone convergence, I actually have that this is actually the limit of these guys. But now look, the LP, now it's the point where I want to use the triangle inequality here. Because the LP norm of this function Hn, remember, Hn was just a sum, a finite sum of functions. Okay? So I'm allowed to use Minkowski here. The triangle inequality. I'm going to say that the LP norm of Hn, since Hn is a sum of n functions, loses to what? The LP norms of these guys separately. G1 P norm plus the sum of gk plus 1 minus gk P norm, k going from 1 to n minus 1. You know, and now comes the point where we actually constructed this subsequence such that the gaps between the consecutive ones was very small, was 1 over 2 to the k, because this is something summable, right? So whatever it's written right here is summable. This is less than 1. This is less than 1. This is less than the sum over 1 over 2 to the k, okay, from 1 to infinity. And then it doesn't depend on n anymore. So what you get is that this h, this function h that you constructed has LP norm that loses to the LP norm of 1 of G1 plus 1. Okay. Actually prove this. So in fact, so this implies that then this function h that you constructed here actually belongs to LP. Has a finite P norm. Good. Okay? Good. So far, so good? Now, this is not the function that we want. This h is not our limiting function. We just have to start it with it to put the absolute values on things to try to bound this thing, which is kind of the worst possible scenario. Everything has the same sign. So the fact that h belongs to LP implies something which is very simple. So this implies, so if my function h belongs to LP, that's the integral of h to the p is finite. So this implies that the measure of the set of points x in omega, such that h of x in absolute value is equal to infinity, this set has measure 0. So if my function has the integral of h to the p being finite, the set of points where h, modulus of h, takes the value infinity has to have measure 0. Okay? So in turn, this implies that, well, but remember, h of x was just the limit of these sums. Okay? So what I'm trying to say is that this sum, so then this sum here, okay, from 1 to infinity of jk plus 1 of x is finite mu almost everywhere. Okay. This sum that defines h, my h is the limit, so it's just the sum up to infinity. So the sums of these absolute values will be finite for almost every point x. Okay. Now, what you can do, once you have proved this, do the following. can do the following. Ta 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 ta. You now observe the following. Observe that Gn of x equal to G1 of x plus the sum from k1 to n minus 1 of gk plus 1 of x minus gk of x. Now the novelty here is that I removed the absolute values, okay? I removed the absolute values. So I'm just writing Gn as the sum of G1 plus the telescoping sum gk plus 1 minus gk. So things will cancel. G1 will cancel G1 here, G2 with the G2, and the last one will be gk plus 1 when k is n minus 1, so it's Gn. Okay? And from this fact here, that this thing here is, this sequence of the sums of the differences in absolute values is convergent, is finite, mu almost everywhere. So I'm summing a sequence of non-negative numbers, okay? So this means that this sequence here is absolutely convergent for almost every x. So if a sequence is absolutely convergent, it is in fact convergent when you take off the modulus, okay? So then we have a well-defined mu almost everywhere, right? Function, but this is all we care. A function f of x, which is just the limit when n goes to infinity of Gn of x. Okay. In other words, for every x such that the sum in absolute value is finite, and for every x such that G1 of x is also finite, which is a full set, this thing here will have a well-defined limit when n goes to infinity. And this is what we call the function f of x. I claim to you that this is our desired f. So my claim is that this is the f we seek. This is the f we were looking for. So we have to prove two things. Well, first, observe that f being a limit of something, limit of measurable functions, f itself is a measurable function. Okay, so f is a measurable function. Second, we have to prove that this f belongs to the space. Remember, we have to prove this f belongs to my space, and we have to prove that my sequence, my overall sequence, converges to this f. That f is actually the limit of the sequence. How do we do that? Let's see. Okay, how do I show that f belongs to LP? Now you observe the following.
We estimate f via hash.
Yes, it's kind of written here on the board, right? So note that each of these Gn, of course, in absolute value, you take the absolute value of Gn, you take the absolute value here, and you use the usual triangle inequality, loses to Hn. Hn was this. It was already positive. Your Hn, for all n's, ends up on H. Hn loses to H. So what you have here, and H belongs to LP. Okay? So if you want, you can actually say that Gn the P loses to Hn to the P, which loses to H to the P. And H to the P is a function that is in L1. So you have the hypothesis here to use the dominated convergence if you want. Right? So your functions Gn are dominated by a function which lies in L1. Okay? So you can certainly say, either by dominated convergence or by Fatus Lemma, whatever you want. So dominated convergence, let's pick it. Convergence tells me that the integral of f to the p is actually equal to the limit, when n goes to infinity, of the integrals of n to the p. And these all lose to the integral of h to the p, which was finite. Okay? Again, you have a dominated sequence converging to a certain function. So the integral of the limiting function is equal to the limit of the integrals. Okay? You could just have used Fatus Lemma if you preferred, just to get an inequality here. Because this is just to say that my function f belongs to LP. Okay? The integral of f to the p is finite, so my function f belongs to LP. Okay, so I have successfully constructed a function that belongs to my space, that it's a good candidate to be the limiting thing. So now this is what we have to do. Finally, we have to show that Fn, your sequence converges to f in LP. Okay. This sequence converges to this function in LP is the same as saying that, remember, this is the same as saying that Fn minus f in LP goes to 0. Okay? But now the thing is, given, so in fact, given epsilon bigger than 0, you can find an index n0 of epsilon, such that Fn minus gk is less than or equal than epsilon whenever n and k are bigger or equal than n0. So remember, this gk is just a subsequence of your fn's. Okay? So if I give you epsilon, this is the Cauchy condition on the sequence. There is an index n0 such that when your indices n and m are very large, I'm taking even the index of gk very large, these two functions are close at the distance of epsilon. So now you look at this expression. The good thing about having to work with Cauchy sequences is that you have two free indexes here, and you can freeze one and let the other one roll. And this is what we're going to do. So this holds for every n and k bigger than a certain n0. You fix n, and you let k go to infinity. So you let k go to infinity, and you may apply now Fatus Lemma if you want. Okay, if you apply Fatus Lemma, what you get is that the integral of the limit. So what's the limiting function of gk when k goes to infinity? It's my f. This thing loses to the limit of, when k goes to infinity, of the integral of fn minus gk to the p. But this was all less than or equal than epsilon. Epsilon to the p, if you want. Okay, so if you just want to take square root p. In other words, what you get is that Fn minus epsilon to the p loses to this epsilon, or n bigger than n0. Okay? This is exactly what we needed to prove. Given epsilon, there exists an n0 such that Fn minus f in the LP norm loses to epsilon for n bigger than or equal to n0. So this shows that Fn converges to f. Okay, so this concludes the proof in this case. We have constructed a function and proved that this function belongs to the space and it's my limiting function. The first part of the argument, we took the function that we wanted it to be. This is the function that we wanted it to be. But we have to put the absolute values just to prove that this function here belongs to LP, so that this sum is well defined almost everywhere. And then we used again to show that this function f here belongs to LP. Okay. Now remember that we have split the cases, right? We were considering the case p strictly less than infinity. Now it remains for us to consider the other case, p equals infinity, which is actually simpler. Okay, so the case p equals infinity, well, remember, you have a sequence Fn contained in L infinity, which is a Cauchy sequence. Okay? So you can say, you can say that the following inequalities, so you can say that Fn of x loses to the infinity norm of n, and that Fn of x minus Fm of x in absolute value loses to the L infinity norm of Fn minus Fm. For all x outside a set of z such that the measure of z is 0. Okay? Remember, when a function is an L infinity, the value, the pointwise value at all points loses to the L infinity norm except on a set of measure 0. Okay? So then you take a countable union of sets of measure 0. So you take for each n the set where this does not happen, it's a set of measure 0. You take the unions of all these guys. And also for each pair n and m, you take the set where this does not happen. It's a set of measure 0. You take the countable union of all of these guys, call it z. So for any x outside z, you have these pointwise inequalities here. Okay? So this means that for any x outside z, since you have this condition here, pointwise, the absolute value of Fnx minus Fm of x loses to this, and this is a Cauchy sequence, so this guy is going to 0, you have that the sequence Fn of x is a Cauchy sequence. Cauchy sequence of real numbers, and therefore Fn of x converges to a function that we call f of x. Okay? And there you have it. So this f of x, we have to prove that this function, which is in principle defined just almost everywhere, but this is all we care. We have to prove that it belongs to L infinity, and that my sequence converges to this function in the L infinity norm. Well, but this just follows from this thing here, right? So if you understand, say, well, given epsilon bigger than 0, there exists n0 such that for m and n bigger or equal than 0, you have Fm of x minus Fn of x losing to Fm minus Fn infinity, and this loses to epsilon. Okay, so this holds anytime you are outside the set Z, and this is the Cauchy condition on the sequence Fn minus Fn. So now what you do is you fix one, you fix m, and let n go to infinity. What you get is that Fm of x minus Fn minus f of x less than or equal than. So this will imply the two things that you want. So this is for all x outside of the set Z, and this m bigger or equal than this n0. So, but this thing implies, well, this plainly implies that first thing, f belongs to L infinity, because the distance from f to a function in L infinity for almost all points, just pick one m, fix this m, and then the distance from f to this function is less than or equal than epsilon, so if this function is in L infinity, so will f be, and this also implies that fm will converge to f in L infinity. Proof in this case is actually much simpler, you know. You kind of have an uniform convergence. Once you throw away this set of measures 0, you have a uniform convergence independent of x. You know. Okay, so this concludes the proof of the theorem. Okay, so this is what we have gained. So now these LP spaces are Banach spaces. Okay, so this is the lesson you have to take from the class today. Okay, let's move on in our discussion. Now that we have proved this thing, so you really have to, at this point, take a look at the book, your favorite book, and solve lots and lots of exercises to get used to these function spaces. Okay. I want perhaps to conclude the class today. I have a few other facts to mention about LP spaces that I will start today and conclude in the next class. But let's discuss a few things about duality. So the LP spaces, this duality between the conjugate exponents, it plays a very big role. And you're just starting, if you're seeing this for the first time, you're just starting to understand this now, but this will go through and through, especially when you do your functional analysis class next semester and starts to learn more about PDEs and so on. But one thing that I want to mention to you is the following proposition. So this LP norm, if you write it on the board here, integral of f of x to the p dx raised to 1 over p, this seems a highly nonlinear object, you know? How do I integrate f of x raised to the p? What if p is not an integer, if p is 5.2? This seems to be a very nonlinear thing, you know? And for some problems, if you want to think about it in a more linear way, there is a way to relate the norm with by making the product with the function in the conjugate space. Okay, so let me call this this duality property. So let's say, let's prove this. So let 1 less than or equal than p less than or equal than infinity, and f be a function in LP. And I claim to you that the following magic thing holds. The norm LP of f is the supremum over the integrals of f times g. And remember, this is with a measure d mu on a space omega. Over all, the supremum taken over all g's that belong to LP prime with norm of g in LP prime less than or equal than 1. this in mind. Okay? So now this highly nonlinear object, if you just integrate in f against some functions g, you can make it into a linear, you have a kind of a linear expression for it, You can take g here, you can take g plus h, sum two functions g1 and g2, multiply by scalar, whatever you want on this right-hand side. And the second part of my proposition is that if 1 is less than or equal than p, and this is less than infinity, this supremum is, in fact, attained. Okay, so therefore, hence, it is a maximum. Okay. Let's see if we can prove this. This will conclude the class today. Proof. Well, let's consider the two different cases. So let's first consider the case 1 less than or equal than p less than infinity. Okay? Well, before that, before we split that, one of the sides is trivial. Okay? One of the sides of this inequality is trivial, because if G belongs to LP prime, norm of G LP prime is less than or equal than 1, by Holder's inequality, you have that the integral of fg, which is this guy here on the right-hand side, loses to norm fp times the norm gp prime. Remember, 1 over p plus 1 over p prime is 1. Okay? I don't have to be writing all the time. 1 over p plus 1 over p prime is 1. And since I'm assuming that the norm of G in LP prime is less than 1, this loses to LP norm of f. So whenever you integrate f against the function g with these properties, the integral is always less than this. The integral, if you want an absolute value outside. The absolute value of the integral loses to the integral of the absolute value, and this loses to these things. Okay? So therefore, you have one inequality. The sup of these integrals loses to this supremum certainly loses to this guy. We have to prove now the reverse inequality, that we can choose a function g such that we can get very close. Okay? But this is certainly less than or equal than this value. Okay, for the other part, let's split in two cases now. Let's consider the case, say, 1 less than or equal than p less than infinity, and then the infinity case separately. And the idea, so for this case, is to pick a function g that does a very good job. So if you look at the expression, if you want the integral of f times g to be the integral of f to the p, so this is what you want to make, right? You want to make the integral of f times g to be roughly the integral of f absolute value to the p. Well, f absolute value to the p, first you have to take a look at the signs, right? Because you don't want f and g to have different signs. And also you want to make it to be f to the p. So if you just forget the sign for a little bit, you want essentially g to be f to the p minus 1. So you have f to the p minus 1, you get f to the p. So you want essentially g to be f to the p minus 1, and you want to adjust the sign. And this is exactly what we are going to choose. So let us choose g, let's say g of x, to be, I want to put here, let's say, modulus of f of x to the p minus 1. That's great. So I have modulus of f of x to the p minus 1. Now, I want to multiply by f, and I want to get the modulus of f. So what I will put here is the signal, or signum, of f of x. Okay. And the signum has to be understood in the following sense. Okay, so for real numbers, you just define the function signum of x to be 1 if x is positive, 0 if x is 0, and minus 1 if x is negative. So this is the signum function. In particular, signum of x times x is always absolute value of x. Professor, how about if I'm working with complex numbers? Sometimes my functions, my vector spaces, it will be interesting to consider complex numbers. So you have to find a way. You can also find a way to do this. So this is, if the signum function is just something of modulus 1 that aligns the signal, okay? So if you are over C, what you would do so over C, remember, this is the inequality that you want to have. Signum of Z, Z is a complex number, times Z, you want it to be absolute value of Z. So in some sense, you will define signum of Z, you just baptize it to be what? You will just put it Z bar over Z. That's what you have to make. If Z is not 0, and the signum of 0 is 0. So you define it like this. Z bar over absolute value of Z. And then when you multiply Z bar, you get normal absolute value of Z square. You cancel 1, you get absolute value of Z. So this relation is always there. Okay, so our function is well defined. Is g of x is signum of f of x, whatever this number is, if it's real or complex, times the modulus of f of x to the p minus 1. So this guarantees that when I multiply this g by f, I will have f of x times signum of f of x, which will be the modulus of f of x. So this is almost what I want. I have to divide by somebody just to make it with the norm 1. Okay? So I will divide by somebody here. Let's see who this somebody is. Let's first check that this function, divide by a constant, c. Okay? So this will be my function. Signum, this is always a real or a complex number of modulus 1. So times the function, f of x to the p minus 1, over a constant. Let's first check that this function actually belongs to LP prime. Okay? So remember, 1 over p plus 1 over p prime is 1. So we have found that p prime is p over p minus 1. So first, the modulus of g is equal to the modulus that g to the p minus 1. And my claim to you is that this belongs to LP prime. In fact, let's try to do the integral of g, the norm, integral of g p prime, 1 over p prime. So this would be the p prime norm of g. That's the integral of f to the p minus 1 to the p prime over 1 over p prime. So this is the integral of f. P minus 1 times p prime is p. That's great. Over 1 over p prime. And this is the norm p of f raised to the p over p prime. Okay? Since this number is finite, because we are assuming that our f belongs to LP, this G will belong to LP prime. So this G is where it should be. Moreover, I actually computed the norm. The norm P prime of G is actually this number. So this is the constant that I am going to come here and divide it by. So I'm going to divide it by this number, which is the norm Fp raised to the power P over P prime. So this choice of G, let's call it star. So this is my G. G is not this one anymore, but with G now as in star, what you get is that the norm of G, P prime, is 1. And now let's do it. What's the integral of f times G? Well, the integral of f times G is, this was constructed in a way that constant, the constant C, which is this, comes out of the integral. And then f times G was constructed in a way that this is modulus of f to the P. Right? Because G has the signum of f. So when you multiply this numerator of G by f, you get signum of f of x times f of x, which is just modulus of f of x, and then another modulus of f of x to the power P minus 1. So you get the modulus of f to the P. Well, and we know what this is. The integral of f, modulus of f to the P, is just the LP norm of f to the P divided by P over P prime. So now you have to make the cancellation. When you cancel this, you get P, the exponent P minus P over P prime. This is, again, P minus P. Who is P prime? P over P minus 1. And again, this gets to be 1, as we want it, right? So this is actually So really, this is the way we actually constructed a function G that lies in LP prime, has norm not only less than or equal to 1, but has norm 1, and such that the integral of fg is actually equal to the norm LP of f. Well, it would be obvious that the integral would have to be 1, because if the integral were strictly less than 1, you could just multiply by a constant, and you would get something better. So in this case, 1 less than or equal than p, strictly less than infinity, we actually proved this stronger statement, that the supremum is in fact attained. It's a maximum. I can actually construct a function that realizes the supremum. Now let's take a look at the other case. Let's take a look at the other case, and then we finish. So the case p equals infinity, this part is the same, right? I mean, the part to prove that this supremum of the Holder's inequality, supremum of f times g loses to the infinity norm of f, continues to hold. Now I wanted somehow to replace this thing. And you see what's the obvious problem here, right? I cannot simply just choose g to be signum of f times modulus of f raised to infinity. So you cannot just plug in p equals infinity in here, right? But ideally, so just think about it, what you want to do. What you want to do is, if your function f were like this, for example, L infinity norm is this thing, this number, n. So you would just need to take a function f that is supported very near this thing here. So you just take a function which is kind of like this. So when we integrated f against g, the support of f just exists when g is the support. So this would be your g. Support of g just exists when f is near the supreme. Right? So formally, what we have to do is the following. So let alpha be a number less than the L infinity norm of f. Take any number which is less than the L infinity norm of f. Well, if the L infinity norm of f is 0, then the function is 0 almost everywhere. If f is 0 almost everywhere, of course you have an inequality. This is 0, and the integral of 0 against something is always 0. Okay? So let's assume that the L infinity norm is not 0, and take any real number which is less than the L infinity norm of f. And, well, if a number alpha is less than the L infinity norm of f, this means that the measure of the set of points where modulus of f of x is bigger than alpha, bigger or equal than alpha, is strictly positive. Okay? The measure of the set, so if alpha is somebody, so if this is your function, if this is the L infinity, I'm saying I'm taking an alpha which is less, so the function will have points, the set of points where the function is bigger or equal than this alpha has positive measure. If this were not the case, then alpha would be the L infinity norm, or the L infinity norm would be less than or equal than alpha, a contradiction, okay? So if you take any guy less than the L infinity norm, the measure of the set of points in omega such that modulus of f of x is bigger or equal than this alpha has positive measure. Now, the measure of the set could be infinity. Right? So ideally, so if we label this set here E alpha, let's call it E alpha, the most obvious thing for us would be to construct G to be the characteristic function of this E alpha. But this is not necessarily in L1. So this G has to be in LP prime. And if P is infinity, P prime is 1. So this G, if you just take the characteristic function of a set, you don't get to be in L1 if the set might have infinite measure. So what you want is to, you want to consider, okay, so just take a subset E contained in E alpha such that the measure of E is strictly positive but finite. You see, this is a little bit of where measure theory might get sometimes technically complicated. You have a set which has positive measure. If the measure is finite, then you're okay. You can choose the set E to be the set itself. But if the measure is infinity, so if you have a set whose measure is infinity, can you always take a subset still with positive measure but finite? This might not be the case, you know. There might be, you have to make a further assumption here, okay? So this is why in some instances like this, you need this assumption of your space being sigma finite. So let's for simplicity here, let's assume, and this is the only part that we use, that our measure mu is sigma finite. You might have examples of measure spaces where there is a particular set that has measure infinity with no subsets of finite measure. Okay? But if you assume that your space is sigma finite, meaning that you can decompose your omega as the union of kn's from 1 to infinity, all of the kn's with finite measure, then your E alpha will be the union of kn's intersection E alpha. And since this guy has infinite measure, you know, one of these guys will have positive measure, but since each of these guys has finite measure, the measure will be also finite. Okay? You can actually take the kn's an increasing sequence if you want. Okay, so this is okay if we assume, for example, that our space is sigma finite. Now, when I have constructed a set E such that inside this E alpha, such that the measure is positive and not infinity, you are free now to take the function G as you took there. You just take G of x to be signum of f of x times the characteristic function of this E divided by the measure of E. Remember, the L1 norm of the characteristic function of a set is just the integral of the function on that set is just the measure of the set, okay? So now when you take this function here, and then you do the integral of f against g, of your f against g, against this g, this is the integral of, in omega, this is the integral of, well, f times signum of f of x is modulus of f, and times the characteristic function of e, divided by this 1 over measure of e. All right? So in some sense, what you're saying is that you get 1 over measure of e in the integral of modulus of f in your set E, right? This is the definition. When you integrate a function times the characteristic function of a set, we can just say that we are integrating over that set. And now something nice happens because in that set, your modulus of f is bigger than alpha, okay? So this is bigger or equal than alpha over measure of E times the integral of the function 1 over the set E. Well, the integral of the function 1 over the set E is just the measure of E. Okay. Get this cancelled, so you get alpha. And this is enough to conclude, because for any alpha less than the infinity norm, we constructed a G that is in L1. It's important that the characteristic function, the set has finite measure, to be in L1. We constructed a function g in L1 such that the integral of f times g was bigger or equal than alpha. Therefore, the supremum over all such g's has to be the L infinity norm, since this alpha was arbitrarily close. Okay, so this concludes the proof. Okay, so let's conclude the class here today. There are still, I want to still continue the discussion on LP spaces in the next class, but this was a good enough start. So today we proved this, well, we recall this first basic inequalities, Holder's inequalities, and Minkowski's inequality. So Minkowski is just the triangle inequality that makes the LP norm actually a norm. And then you have a normed vector space. The next step is to prove that it's actually a Banach space. We proved that it's complete. And we now investigated this a little bit further, this duality property between LP and LP prime in terms of the norms. Okay, so take this property. This will be heavily useful for you in the future. All right, we finish it today. You guys have a good weekend. I will try to assign to you the next homework by the end of the day. Class is over, guys. Bye-bye.